Hello everyone. This presentation is to share my experience on satellite-based augmentation service or SBAS exploration in Thailand. By augmentation, it means adding or enhancing. Enhancing what? It enhances the positioning accuracy from GNSS so that the positioning accuracy is improved from the normal one, which is around 10 meters to 1 to 2 meters. Here is the general pictures of SBAS. To have SBAS service, somebody has to invest on a reference stations and then keep observing the signal, the GNSS signals 24/7, transmit this observation, the raw observation to the master control station, and at the master control station it calculates corrections which compensate for the signal delay due to the Earth's atmosphere, and then upload this correction to the SBAS satellite. Then the satellite broadcasts down the correction onto the Earth. The GNSS receiver, if they are capable of decoding the correction message from SBAS, then the positioning accuracy can be improved. Here is the existing worldwide SBAS. So far we have Europe, EGNOS in Europe, GAGAN in India, MSAS in Japan, and VAST in the US. There are two more coming soon, which is SDCM from the Russian and BDSBAS from China. For neighboring country like Thailand, we found that we can still receive the signal from the nearby country, which is India and Japan. So that we raise the question if whether or not the SBAS signal that we see are they useful for Thailand? If so, how much positioning accuracy can be improved for Thailand or some other similar country who is the neighboring to this existing SBAS country? Here is the receiver that I explore. I try Android smartphone, two models, Huawei and Zenfone. I try iPhone 6s, and I also try a professional grade receiver, which is U-Block, the model M8N. The cost is $179 plus shipping and tariff. Here is the spec comparison. Huawei and iPhone 6s are able to receive the signal from GPS and GLONASS. This is from the Russian satellite. For Zenfone 2 and the U-Block, they are able to receive up to 4 constellations with GPS, GLONASS, Beidou from China, QCSS from Japan, and these only two model, which is Zenfone and U-Block, they are able to decode the SBAS message, meaning the positioning accuracy of these two receivers should be improved. To measure the accuracy performance, we need to set up a reference point which should have a very precise very precise position. We use RTK survey, which is able to provide 1 to 2 centimeter accuracy. We get support from the Topcon Thailand for the RTK survey grade receivers, and we also have the RTK correction message broadcasted by Department of Land Thailand. So thank you for these two organizations. We place the RTK receiver on the pole over here. As you can see, we use this pole as a reference location, and then we measure the position. of the pole over here. So after we have a very precise position of the pole, then we place the 4 receivers on top of the pole and then perform data collection for around 10 minutes. Here is the result. We have 2 sides, which is accuracy and precision. For accuracy, we use root mean square speed RMSE to measure. We compare the points collected with the reference points. As you can see, U-block, as expected, U-block and Zenfone deliver the best positioning accuracy. They are able to use the SBAS message. The U-block delivered 1.6 meter accuracy and 3.7 for Zenfone 2. For in terms of precision, we use circular error probable at 95%. By circular error probable, it means finding the smallest circle, the radius of the smallest circle that is able to cover up to 95% of the points collected. In this case, U-block again have the smallest circle at 2 meters radius. Zenfone is the second best, iPhone, and then Huawei. Here is the spatial distribution of the point collected. The green triangle is the reference point. Here the gray color point is from U-block, and the blue is from Zenfone. The iPhone is the red star, and the yellow dot is Huawei. We have 2 interesting observations. Over here, for the first 2 seconds for Zenfone, the points are far away, but after 2 seconds they move closer to the reference locations. And the similar things happen to iPhone 6s, but it takes up to 10 seconds to move closer to the reference. Here is the point that are moving closer. Another interesting observation is that the number over here 118 and 226, 294, 65, for example, here is the number of points. The number of points that fall on the exact same location to the previous point. This means the 2 phones having some saving algorithm, energy saving algorithm. They try not to recalculate the position when they detect that the phone is not moving. This is good in terms of energy saving. For Huawei, it doesn't have this kind of algorithm, so the point just keeps gathering around the reference location. Let me show you this clip. This video clip show you the position from Zenfone, the yellow one, and Huawei position. And remind you again, both phones are placed on the same locations, and you can see the points are just moving around. Zenfone 2 has a very much smaller range of point moving. Let me go back to the presentation. Okay, here's the conclusion. SBAS correction is useful to Thailand. We can achieve 2 meter CEP 95%. Zenfone 2 provide best positioning accuracy. Before I finish my presentation, let me raise an open-ended questions, which is, okay, now we know SBAS is useful for us, for the developing country. So how should we set up our directions? Should we collaborate with the existing country having SBAS, or should we just invest on our new own satellite, or should the developing countries cooperate together and invest or share on the SBAS satellites? Okay, this one will be a future discussion topics and very important. Okay, bye bye.